Good morning, everybody. Thank you for joining this second webinar, part of the ZHENIT E-learning program. Today, I'm here with Lorenzo Ciappi from the University of Birmingham and Adriano Sciacovelli from the University of Denmark, and they will tell us more about the optimized waste heat recovery. I just wanted to remind you all before leaving the floor to our speakers that this meeting is being recorded. So if you want to watch the webinar again, you can in the upcoming days. We will upload the recording on our YouTube channel as well as our project website. So follow us on our social medias and you will be updated there when it's available. Okay, thank you. And I'll leave the floor to Lorenzo and Adriano.
Right, thank you. Thank you very much. My pleasure. I'm going to share my screen straight away. It's my pleasure to join this event of our fantastic project ZHENIT. My name is Adriano Sciacovelli, and I'm professor at the Technical University of Denmark and honorary professor at the University of Birmingham, where I've been, let's say, contributing, leading some of the activities in this project. And we are very pleased to share some of the learnings that have emerged from one of the many aspects around this project specifically. So I have a bit of an outline here of what I would like to bring to the table as lessons learned and where the frontiers of our research has brought us and as a whole, as a project. So really three key aspects around these hidden, sometimes not so hidden resource of waste heat on board and how this relates to decarbonization of the maritime sector, how that can be valorized and recovered to some extent with a system level thinking and approach that we are advancing and proposing, and some element around what excites the most, at least from our perspective, which is around enabling technology like thermal energy storage for onboard applications and not only. So I'll spend 25 minutes on these. It's going to be a bit of a running through, obviously, and hopefully spark some good conversation. So maybe before getting into this aspect, it's important for us to emphasize where our role and expertise lies. So we focus on fundamental understanding of thermofluid processes and phenomena. We intend to exploit them for developing new technologies and methods, usually for rational and efficient use and storage of thermal energy. So there are really two key areas, two domains. One, diving into the fundamentals and into what can be, let's say, understood better, so that more in a bottom-up approach, new solutions, technologies, and approaches can be developed in a range of contexts, and obviously in ZHENIT for what concern the decarbonization of the maritime sector and of onboard use of energy. So I'll start from this side, from this application-oriented point of view, because usually, as I will talk about, there are many alternatives and there are many competing solutions, and we need to understand first whether what we developed, so what is on the left-hand side, makes sense from an end-use and application point of view first and foremost. So the first question and the first aspect and learning that has emerged is what are the extent of these resources on board in terms of waste heat, and how much of this can be valorized and potentially can be exploited. So that's collected in a number of outputs and activities that are available both in publicly available proceedings and publications from us. So we looked at a holistic approach and focused particularly first and foremost in this characterization of the sources of waste heat. And that was one of the first learning in this activity. So a cascade of waste heat resources from a high temperature to medium intermediate temperature and low temperatures waste heat resources. So primarily, obviously, from the engine, from the propulsion. And what has emerged and what is interesting is, first of all, that there is this cascade of resources, which often has been not necessarily seen and considered in an integrated fashion, and that's what has been done in this project as well, and how they can interact later on with the downstream recovery options. What I would like to emphasize, and one of the learnings, that these waste heat resources, first and foremost, are spread across a range of temperatures. So what you see here is to a good extent analysis around real data from engines, from manufacturers, current onboard engines, as well as from modeling activities available in the literature. And what you see is a cluster of three main temperature levels and resources, from let's say low temperature around 50 to 70 degrees C, around primarily oil and lubrication loops, and progressively to higher and higher temperatures, and up to potentially 200 degrees C or so, which is primarily from the stack of the engine. What is interesting is that first and foremost, there is this spread of temperatures, and there is between themselves quite a bit of a range of dispersion. So the ability to capture these temperature levels, as well as the variability of those, is one of the key learnings out of these activities at system level. But also to correlate that to the speed and to the engine performances, because what you see here is obviously a characterization of a specific quantity like temperatures, but we are most often interested in the amount of waste heat that is available and how this changes dynamically with the engine load. And this is what was captured in these system level activities. So, as I mentioned, the dynamic aspects are one of the key emerging ones from the learnings of these activities in this part of the project, where the waste heat resource is not only relevant in its temperature levels and in its extent, but also in relation to the voyage of the vessel. So what you see on the right-hand side, this is more from time series analysis and a correlation between the journey of the vessel and those resources, is that those resources are not necessarily always available. They are always strongly correlated with the journey. And very importantly, they are, let's say, they're available for recovery in current engine technologies, but even under the fuel switching scenarios, where more sustainable fuels might be utilized on board, this waste heat remains a quantity and an energy resource that requires to be properly addressed, even in those scenarios. And that was captured in one of our recent work and publication on this system level analysis. So we have resources, we have dynamics. The key question and key activities, how we link those, how we let's say recover those resources, how we mitigate those intermittencies. And this is where we proposed and developed a system level approach that looks at trying to capture the effect of multiple technologies, particularly the ZHENIT technologies. Obviously, there is a different multiple technology that could be deployed on board, but we focus obviously on those that were in the scope, particularly of the project. So we're talking about 3 active technologies. This means conversion into useful effect, like organic Rankine cycle with integrated ejector technologies for cogeneration, absorption plus for cooling and desalination, isobaric expansion engine, which is another waste heat to power conversion, and an enabling technologies, which is thermal energy storage. So I appreciate that there are more than these. This is the focus and the, let's say, scope of the activities, particularly this project, and therefore the learnings out of this element of the project. So as I mentioned, although the characteristics on the right and on the left-hand side of the waste heat sources are quantifiable, as I just discussed, and replicable, I would say, across other onboard and other vessels. So we look at a number of representative cases, particularly from cruise vessels as well as from cargo ships. The fundamental question is how these integrated technologies downstreams could dynamically recover those waste heat resources, and how that can be done optimally in relation also to the voyage of the vessel. And optimally, for our purposes and our interests, has been primarily a thermoeconomic optima. So economical optima as well as efficient optima. And I'll show you a few of the learnings that have emerged here. What you see on the right-hand side is our superstructure, our abstract representation of the cascade of waste heat resources and the possible technologies and integration location for the technology. So you notice here that there are high, medium, and low temperature thermal storage, high, medium, low temperature potentially organic ranking cycles, absorption systems, absorption plus desalination, and isobaric expansion engine. The framework that we developed is a forecasting and predictive tool that allows us to understand whether, first and foremost, these technology needs to be there. What is the capacity, i.e., how much of this technology should be deployed, given the characteristics of the waste heat sources, and also how they should operate with respect to the voyage of the vessel, as well as of the availability of waste heat. That's the framework that we developed. I just give you a let's say overarching view of the approach and methodology that is detailed more extensively in our recent outputs and publication from the project itself. So we have three main ingredients here. As I mentioned, a superstructure. This is a typical approach for what concern multi-energy systems analysis. So a series of options that might become active with respect to deployment of these waste heat recovery technologies. And we are trying to understand whether they are indeed relevant and to what extent. So that means that they need to be optimized and they need to be properly represented in a series of optimization and modeling techniques. We use a combination of thermodynamic modeling plus mixed integer and linear programming modeling. This is to allow characterizing the thermodynamic performances as well as the operability of these technologies. And as an output, as I mentioned, various decision-making matrices, meaning to what extent this technology should be deployed, what's their capacity, what's their obviously ultimately the cost that they will incur into, and ultimately how much of the resource of waste heat is recovered and valorized. And our approach has been typically to minimize the upfront investments in these technologies, as well as the operability, where particularly the energy storage comes into play here. So I'll give you again some exemplar cases, some exemplar results of this approach. So what you see on the right-hand side is this picture of waste heat availability against the time of the day, or the days of the voyage, pretty much. And you can notice in blue also the vessel speed, which obviously means indirectly a certain power output from the engine, and therefore an amount of waste heat available. So this goes beyond what is typically done in the literature and in the analysis of this type, where it's usually a snapshot at a point in time rather than over the entire journey of the vessel. And this approach is highly replicable in various other contexts, particularly in industrial systems. So this, let's say, one of the outcomes of this methodology, the ability to predict or to estimate waste heat available over time, and then how that obviously feeds into the methodology that I mentioned before, the optimization and the decision making with respect of the technologies themselves. So what the framework that we propose, and that is discussed a bit more in detail in our recent paper in Applied Energy, allows to first quantify of these bands of waste heat available at a certain point in time, so medium to low to high temperature waste heat, how much of that optimally could be recovered, means either stored or converted in other forms by those four technologies: the thermal energy storage, the organic ranking cycle, the absorption absorption cooling and desalination, as well as the isobaric expansion engine. Obviously, there is always an amount of unused waste heat, because some of those technologies, like the ORC, are obviously conversion cycles, so they naturally have to reject a certain amount of waste heat at a lower temperature. That's dictated obviously from first principles of thermodynamics. So most of the recovery could happen, more than what is currently done with traditional processor integration, pretty much of onboard waste heat. But there is obviously a remaining amount of low-grade heat that remains not capturable, at least with this portfolio of technologies. And as I mentioned, obviously, not only with respect of individual days, but with a higher granularity, so of time. So in this analysis and this approach, we look at forecasting optimization with a time increment that could range from 15 minutes to 30 minutes as a minimum time steps, but to doing over multiple days of the entire journey of the vessel. So what we concluded, or what are some key take-home messages? That for a certain range of deployment capacities of those technologies, so what you see on the left-hand side is, for example, what's the nominal capacity of ORC optimal one that would be deployed or could be optimally deployed on the reference vessels that we looked into. Similarly for the other technologies, as well as for the thermal storage capacity of the thermal energy storage. This system-level approach compared to the individual interventions that have been proposed and investigated in the literature, like an individual deployment of ORC or individual deployment of storage or other technologies, allows better dynamics between the technologies themselves during operations and between the portfolio of technologies and the waste heat sources. And that, based on our estimations, leads to a greater fuel saving compared to what is available in the literature. These spreads that you see here are from available other attempts to recover waste heat and discussed in the literature, and these spreads against our results are the sensitivities with respect to our input parameters. So we have a greater fuel saving and potentially some relatively reasonable improvements in the economics. Still, these technologies remains to some extent at pilot scale and not yet fully commercialized, some of them in particular, like the thermal energy storage. And therefore, there is a learning curve that still needs to be understood to decrease a few of the economic parameters of these technologies. So that is a picture at the moment in time with the best estimation available. It might improve in the future as the technology progresses. Remember that in ZHENIT we are addressing TRL 5 to 6 approximately in onboard applications. And these are pretty much also the key learnings. Key learning is to keep a system-level perspective, consider the dynamics into the energy systems on board, and exploit that to achieve better thermoeconomics results from the deployment of these solutions. So I'll spend just a few minutes as a prelude to more conversation around the thermal energy storage, which is one of our core expertise and what excites the most. So I'm moving from the left-hand side, from the right-hand side to the left-hand side. We understood that there is a role of many of these technologies, including storage, how storage should look like actually at a fundamental level if deployed on board. And here we have multiple let's say investigations ongoing and available, as well as in the literature. I just give a quick overview of some of the features that that have emerged as learnings on this aspect. One of them is that obviously there are multiple options for thermal energy storage. The one that we looked more into detail because they probably have the greatest potential are what we call advanced thermal energy storage. So latent heat or thermochemical energy storage, and for the purpose of ZHENIT, particular latent heat. So where we exploit what we call phase transitions, so solid liquid phase transitions of suitable subatom materials within individual components. So we try to exploit this melting and solidification of materials that could match those temperature levels of waste heat, and that they could therefore be on one side, more compact, greater amount of energy for a smaller volume, and as I mentioned, be multi-temperature. So it's a stackable solution that ideally occupies less space on board and allows better matching with those temperature ranges that I just mentioned before. And there are onboard applications, but also learnings that has occurred for other applications. I'm just touching upon the onboard ones. So just to give you a flavor and give you some more hands-on, let's say, feeling of what we are referring to, we are referring to substances, specialized materials that interact with heat transfer elements, and that by melting and solidifying the substance that is between the heat transfer elements, we can store waste heat. This will be solid to liquid phase transition, and when best available, retrieve that heat previously stored for onboard utilization, and that's when this substance will transfer from liquid to solid, or so-called phase change materials. There are many parameters here, and I spend literally 3 more minutes on just emphasizing that the approach that we propose and the way that we go about developing and understanding thermal energy storage is different from the traditional one. We look at what we call topologies and topological approach, or sometimes also called non-parametric approach, meaning we try to explore more extensively what are the opportunities to design these heat transfer elements in a way that is not conventional, i.e. is not just by borrowing traditional heat transfer solutions, but rather to have method that allows to explore more extensively all the design parameters. This means material properties, means geometrical parameters, means operational parameters, such that we can exploit this potential in latent heat energy storage more extensively and go beyond what are some of the bottlenecks that have currently emerged from the literature, namely relatively limited heat transfer performances, as well as relatively high costs. So I invite you to have a look at our previous work and current work, where we have looked at multiple ways and multiple topological approaches to look at how we can configure those heat transfer elements inside the latent heat thermal energy storage. The one on the right-hand side is the one more relevant for the ZHENIT work, and is more sort of plate type with the specific fluid system for storing heat, and that refers to the picture that I showed you before with this, let's say, plate type heat transfer element intercalated with the phase change materials. Here, and I spent, this is my last 2 slides, I want to emphasize that this is a very multidimensional problem. And here we developed various approaches to find the best intersection between multiple parameters. The geometrical one, like spacing dimensions of these latent heat thermal energy storage, as well as thin pitch, as well as other parameters, with the intended end user requirements, which are typically the power output, so how much thermal energy could be released by this storage, or how fast can be charged, and for how long, namely the storage capacity, for how long the storage could indeed store energy. And we have a couple of ongoing publications that will expand on this and present fully how we managed to find a good interplay between geometrical parameters and costs that allows to bring down or to increase the techno-economic competitiveness of these systems at various scales. We usually look at megawatt hour scales. So final remarks to conclude from my side. The key learnings and perhaps some elements that I would like to emphasize for those of you that are in this space of activities is that is always a race between 3 key features and 3 key aspects. The physics of the challenge, so understanding and take advantage really of the thermal processes and phenomena that ultimately are behind the rational use of thermal energy, store of thermal energy, and recovery of thermal energy. Without fundamental understanding of those, we cannot really advance technological solutions like latent heat thermal energy storage. Do not forget the system point of view, namely that regardless which best technology is developed, it will be always part of a broader system and will always interact with other sub-technologies as well as potentially with other competitors or competitive solutions. And namely also to remember that is a thermoeconomic challenge. So that the economics and the rational use of energy is what ultimately very likely dictates winners and losers in this space. So that's all from my side. And obviously, I remain available either now or later on for any conversation and questions. So I'll pass back to the chair of this e-learning, and that's all from my side.
Thank you very much, Adriano. Thank you. I'll leave the floor to Lorenzo now.
Thank you, Martina and Adriano. I will share my screen. Good morning, everybody. I'm Lorenzo Ciappi, and I'm a postdoctoral researcher at the University of Birmingham. I'm going to present you the research that was conducted on the design of a latent heat thermal energy storage for the application on board the vessel. Indeed, on vessels, there is a availability of waste heat that mainly comes from the main engines and the auxiliary engines of the vessel. And this availability of waste heat can be classified in three main levels of temperature, as we have seen. The highest level of temperature is the one of the exhaust gases, which have an average value of temperature of around 270 degrees Celsius and a percent in waste heat allocation regarding the fuel that is about 22%. The second contribution to the waste heat on board is provided by the scavenger that has an average temperature of 150 degrees Celsius and a waste heat allocation in fuel energy around 12-13%. The lowest level of waste heat has a temperature that is below 100 degrees Celsius, and it's represented by the lubricating oil and the jacket water. Their waste heat allocation is around 5%. The analysis that was conducted considered thermal energy storage based on pillow plates and latent heat transfer. The system comprises a set of plates with a specific geometry that is called pillow plate. As we can see in the image, they have a wavy surface that is obtained by hydroforming to metal sheets that are connected through linear weldings and circular weldings. In this way, it's possible to obtain an internal channel inside the plates that drives the heat transfer fluid inside the plate and increases the turbulence of the fluid itself. As we can see in the image, there are two manifolds, an inlet and an outlet manifold. The heat transfer fluid enters the system through the inlet manifold, which provides the heat transfer fluid supply to each plate, and the fluid passes through the plate following the path indicated by the red arrows. In this way, the fluid can cross the entire plates and exit through the outlet manifold of the system. The pillow plates comprise a bundle through the two manifolds and are submerged inside the phase change material that is contained inside the tank. The principle of operation of the system is the heat exchange between the heat transfer fluid and the phase change material. During the charging phase, the heat transfer fluid releases heat to the PCM, increasing its temperature, and the PCM, during the process of charging, stores heat. Conversely, during the discharging phase, is the PCM that releases heat to the heat transfer fluid, completing this second phase. The geometry that was studied is based on the pillow plates, and there are important geometric parameters that define the configuration of pillow plate. In this case, a total number of 10 pillow plates were considered, and the size has a length of 700 millimeters and a width of 900 millimeters. Other important parameters are the inlet and outlet diameters of the pipe and the plate pipe diameter. What concerns the other important parameters of the pillow plates, these are the diameters, internal and external, of the welding. And a key aspect to define is represented by the distance between pillow plates. Indeed, this parameter determines the process of melting and solidification of the PCM. Reducing the distance between two adjacent pillow plates reduces the time that is required for melting and solidifying the phase change material. However, during the design process, it's important to evaluate this parameter because it can pose constraints in the manufacturing process. In this case, it was considered a minimum distance of 12 millimeters and a maximum distance of 15 millimeters, while the internal gap inside the pillow plate is 10 millimeters. The analysis that was conducted is based on computational fluid dynamics. The domain is represented by half of the size of the pillow plate and the heat transfer fluid inside of it, and half of the phase change material surrounding the pillow plate. This was done applying the consideration that pillow plates have an identical geometry, which is symmetrical regarding the longitudinal axis of the pillow plate. Moreover, the fluid conditions inside the plates are identical, considering each plate due to the presence of the inlet and outlet manifolds, and the heat exchange between the PCM and the heat transfer fluid is considered equal for each plate due to the high number of plates present in the domain and the limited heat losses toward the external due to the presence of thermal insulation. An unmapped mesh was created using 1 million elements and performing a sensitivity analysis from a value of 0.3 million and 3 million elements. The solidification and melting model was applied to solve the thermodynamics of the phase transition of the storage material, and an enthalpy porosity formulation was applied to determine the phase of the mushy zone. The heat transfer fluid is terminal 66 due to its good properties in the heat transfer, while different typologies of phase change materials were considered. Organic and inorganic materials, hydrated salts, and solid-solid PCMs. The definition of the design space was based on the application of the latent hypercomb sampling, and a set of 100 configuration was obtained by considering 4 parameters. For what concerns the PCM, the melting temperature and the latent heat were varied, while for the heat transfer fluid, the mass flow rate was considered in its variation, and different levels of charging temperature were considered. For each randomly generated parameter, the correspondence of the desired parameters with the commercially existing PCM was evaluated. Here we can see the processes of charging and discharging of the system. The charging phase starts with the thermal equilibrium between the phase change material and the reference temperature at 20 degrees Celsius. Starting with the charging phase, the heat transfer fluid starts to release sensible heat to the phase change material, which increases its temperature, undergoes the melting phase, and then again increases its temperature until reaching the equilibrium with the temperature of the source. During the discharge, the PCM releases sensible heat to the heat transfer fluid initially. It reduces its temperature, solidifies, and then again the temperature of the PCM reduces until reaching the equilibrium with the sink. The analysis was done considering both the average value of the temperature and liquid fraction of the PCM in the entire domain and near inlet. It's visible that near the inlet, the melting and solidification of the PCM requires less time than the average value of the entire domain. A sensitivity analysis was conducted to evaluate which are the effects of design parameters and application parameters. In particular, the temperature of the heat source is linked to the available waste heat on board. So it's a boundary of the application case. And we can see that the increase in temperature of the heat source has a strong effect on the duration of the charging phase of the system and in the energy that is stored by the PCM. This is mainly due to a higher heat transfer, and in particular, the higher energy that is stored is connected with a higher value of the sensible heat below the level of the melting temperature, above the value of the melting temperature of the PCM. The choice of the phase change material is a significant parameter. Indeed, the phase change material has to be selected based on the application case. And we can see from the analysis that was conducted that the specific choice of the PCM strongly affects the dynamics of the charging of the system and the energy that can be stored by the phase change material itself. Another parameter is represented by the mass flow rate. The mass flow rate of the heat transfer fluid has an effect that is limited on the operation of the system. Indeed, if we consider the entire set of the configuration analyzed in the study, a strong correlation between the mass flow rate and the charging time was not found. However, it has to be remarked that fixing the configuration of the system, a variation of the mass flow rate of the heat transfer fluid has an effect on the time required for the charging and discharging of the system. So the mass flow rate can be used to reduce or increase the time for the phase change only when the other parameters of the configuration are fixed. But a general correlation was not found. In the entire set was found that regarding the typology of system of phase change material, so of latent heat, a doubling of the value of the latent heat determines an increase of about 15% for the charging time of the system. Moreover, a regression function was determined to link the charging time and the charging temperature, observing that an increase of the charging temperature of the application case, reducing the charging time for the phase change. The values of the key performance indicators of the entire set of modules considered are reported in this slide. It was found that the average values of the mass of the system is about 500 kilograms, while the average value of the module is around 0.24 square meters, and the energy storage capacity value was found to be 22 kilowatt hour, and an average energy storage density is 90 kilowatt hour per square meter. It has to be highlighted that the configuration of the pillow plate latent heat thermal energy storage module has to be done for the specific application case. So this is a sensitivity analysis that provides the effects of the single parameters, expected effects of the single parameters on the performance of the system, and provides a guideline for the design of the system, but the definition of the specific geometry and the selection of the phase change material has to be done for the specific application case and the specific conditions of the waste heat availability. Then the analysis was scaled up considering the number of modules necessary to operate on board the vessel. A range of the main engine capacity was considered, and a value of modules between 2 and 60 was obtained for the thermal energy storage system. Considering the case with the highest value of the main engine capacity, that is equal to 18 megawatt, it was found that the mass of the pillow plate system is 30 tons and the volume 16 square meters. These two values represent the 15 and 5% respectively of the mass and volume of the marine engine. Moreover, it was found that the additional fuel consumption of the application on board of pillow plate latent heat thermal energy storage is a value that is close to be negligible, and the increase in capital cost of the vessel is 0.2%. This kind of technology can provide a significant effect, as previously seen on the waste heat recovery on board, so their feasibility was positively confirmed. To conclude, what was done was assess the availability of waste heat resources on the vessel, the operation of a thermal energy storage system applying pillow plates was investigated with fluid dynamics, computational fluid dynamics, and the sensitivity analysis was conducted to evaluate the effects of the temperature of the heat transfer resource, the typology of phase change material, and the mass flow rate of the heat transfer fluid. For analyzing the operation of a single module, the key performance indicators were obtained. The mass is about 500 kilograms, the energy storage capacity 22 kilowatt hour, and the energy storage density 90 kilowatt hour per square meter. The results were scaled up to a real case scenario considering different values of capacity of the vessels and the number of modules needed to operate and recover heat, waste heat on board were determined. A current activity that is going to be carried out is represented by the design, assembly, and testing of a pillow plate latent heat thermal energy storage prototype. In particular, the system has already been designed and assembled. The preliminary testing has been conducted on the system, and then the further testing will be conducted once the prototype will be in the laboratories of Tecnalia. This is the scientific publication that was achieved by the group of the University of Birmingham and is on applied thermal engineering. Thank you for your attention, and I'm available for questions. Meanwhile, I leave the floor to the organizers of the webinar.
Thank you very much, Lorenzo, for your interesting presentation. As he said, if you have any questions, we are available to answer. And for now, I don't see any, but in the meantime, I just wanted to remind you, as I said at the beginning of the meeting, that this webinar will be available soon on our social medias and website, so you can access to the presentations and, of course, the recording of the meeting. And yeah, I don't see any questions, so I think we can close the meeting. Thank you very much again, Adriano and Lorenzo, for your presentations, and we will see you in the next webinar for the ZHENIT E-learning program. Thank you very much, everyone. Bye.
Our pleasure. Thank you.
Thank you very much. Bye-bye.
Bye-bye.
Bye.